Take the number 1, then 2, then 3, then 4, and so on, all up to infinity. Now square all of these numbers like 1 square, 2 square, 3 square, and so on. Now just write the reciprocal of all these numbers, meaning write 1 over 1 square, then 1 over 2 square, 1 over 3 square, and so on. Finally, add all of these numbers to get this. What do you think will be the value of this infinite sum? This is called the Basel problem, and for years mathematicians struggled to find its exact value. Then came one of the greatest mathematicians of all time, Euler. What Euler did was absolutely mind-blowing. He managed to find the exact value of this infinite sum, and, to everyone's shock, it was deeply connected to pi, yes, the number that appears everywhere in circles, waves, and trigonometry. Today, let us see how he did it. During his time, everyone, obviously including Euler, knew that the function sine of x can be written in the form of an infinite polynomial as x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. If you don't know what factorial is, then it's just the product of all whole numbers from 1 to that number. For example, 5 factorial is 5 times, 4 times, 3 times, 2 times 1, which is 120. Now this is also known as the Taylor series of sine of x, which is just a way to write the sine function as an infinite sum using simple powers of x. Now here comes the magic. Consider a polynomial or a quadratic function to be specific. X square minus 5, x plus 6 equals 0. We know that we can rewrite this quadratic function as x minus 3 times x minus 2. So we say that this polynomial has two linear factors, x minus 3 and x minus 2. Now if we equate it to 0, we will get the roots of this equation as 2 and 3, right? So the linear factors give us the roots of the function. That is the places where the function is equal to 0. Now Euler thought that this was nice. I can do the same for sine of x. But how? For that we have to reverse engineer by considering what the roots of sine of x are. Look at this graph. The roots of sine of x, or the places where sine of x equals 0, are x equals 0. 180 degrees, or pi radians, then 360 degrees, or 2 pi radians, then 3 pi, 4 pi, and so on. Also notice that we get the roots on the negative side of the x-axis as well, which are minus pi, minus 2 pi, minus 3 pi, and so on. So, we can write sine of x as product of its linear factors, or x minus 0, which is simply x times x minus pi, times x minus this, or minus pi, which will be x plus pi. Then similarly, this times x minus 2 pi times x plus 2 pi, and so on. Now look here, what do you see? We have the form a plus b times a minus b, which we all know is a square minus b square. So sine of x equals x times x square minus pi square times this will be x square minus 2 square pi square times x square minus 3 square pi square, and so on. But now he thought what to do next. He felt he was stuck here. So he thought we would restructure this to make it more convenient. Instead of writing it this way, what if we write x times x square minus pi square as 1 minus x square over pi square? Then this x square minus 2 square pi square as 1 minus x square over 2 square pi square, and this as 1 minus x square over 3 square pi square, and so on. Now suppose x equals 2 pi. Then, if we put it here, we get 1 minus this will be 1, and thus this thing will become 0. Similarly, at all the roots of sine of x, we get sine of x as 0 using this restructured polynomial. Nothing has changed, it's just that he has simply made it more convenient, and in a minute we will see how. Now let us multiply some of these terms, and see what we get. First, consider these two. We get 1 minus x square over 2 square pi square minus x square over pi square, and both of them will give plus x to the fourth over this. Now we will multiply this term that we just obtained with this term. Let us multiply it 1 by 1. This gives us 1. Then this gives us x square over 3 square pi square. Then this gives minus x square over 2 square pi square, and this gives x to the fourth over this. This gives minus x square over pi square, and this gives plus x to the fourth over this. Then finally, this gives x to the fourth over this, and then this gives minus x to the fourth plus 2, or x to the sixth over this. Now, all of these don't contribute anything to our desired result. So we will call them together by some value t. Now also take x square over pi square as common from here to get this as t minus x square over pi square, times this will be 1 over 1 square, plus this will be 1 over 2 square plus. This will be 1 over 3 square. I am getting goosebumps right now. Do you notice anything? Yes, we are getting somewhere near to the Basel problem. If we keep on multiplying this, we will get some power of x, which will be useless for this problem, except for this x square over pi square, which will have this infinite sum with it as the coefficient. We can write this sum as summation n equals 1 to infinity, 1 over n square. Now finally multiply this x to get here something minus x cube over pi square, times this sum. So the coefficient of x cube will be minus 1 over pi square times this sum. But look at this Taylor series of sine of x. What is the coefficient of the x cube? It is minus 1 over 3 factorial. So we will equate both of them to get this. Now this minus sign will get cancelled out and take pi square here to get our required infinite sum as pi square over 3 factorial, which is 6, and that's it. So using this method, after 19 long years of posting this problem, Euler discovered that this infinite sum equals pi squared divided by 6. Let us verify this. Using this simple 4 lines of Python code, I have written a loop that adds up 1 divided by number squared, starting from 1 and going up to 10,000. This is not truly infinite, but it gives us a very close approximation. When we run this code, the output is approximately 1.6448. Now, if we calculate pi squared divided by 6, which is the actual theoretical value of the infinite sum, we get approximately 1.6448. The numbers are almost identical. If we increase the limit beyond 10,000, the result will get even closer to the actual value. Isn't this super cool? So good!